Where we left things in our last discussion was essentially finding ways to utilize the coupling diagram and the coupling matrix to get the filter response that we really want. We have already discussed one method, which, as a reminder, it was related to starting from a low-pass prototype, synthesizing the values of the low-pass prototype, and then scaling everything in the right frequency response as well as in the right type of response. For example, from low-pass to bandpass or bandstop. In this lecture, we're going to focus mostly on the second technique, which, as I mentioned, it has some advantages, primarily because it preserves the coupling diagram. And the reason this technique preserves the coupling diagram is because we actually compute the coupling matrix based on the desired filtering response in the normalized frequency domain. So we still start with the normalized frequency domain, basically of omega is equal to 1, but we're starting from a coupling diagram that basically gives you the response you want. It could be, for example, bandpass, it could be bandstop, it could be dual band, it could be essentially any type of filter that you might need. And then once you do that, the only thing that you have to do at the very end is basically apply scaling in frequency, which is done through the frequency transformation of the bandpass. So the main advantage of the second technique is that, once again, you preserve at the very end the coupling diagram. In order to do that, we have to introduce a new concept, the non-resonating node, or NRN, as I'm basically showing here. And I will discuss this in a minute. But regarding the equations we use to calculate the S21 and the S11 are basically exactly the same as what we had seen before. So remember, we need three matrices. We had the R matrix, we had the U matrix, these are standard matrices, and then we have the coupling matrix M. So let's talk a little bit about the NRN, and I will give you both the general overview of this, and then at the end I'll also give you a very specific layout example so you can see exactly how it looks like. So first of all, it's a relatively new concept. You won't see it in traditional filter synthesis books. It was actually introduced back in 2005. And the main reason people essentially introduced that concept is because it allows you to build very flexible designs. Essentially, it's a modular design idea. So I kind of hinted on this last time a little bit, but it essentially is an idea where you can cascade, you can connect nodes to each other, and essentially is a very intuitive concept. As we'll discuss examples, I'll give you explicit ways of thinking what the response of a coupling diagram is without even doing any calculation. So it's very powerful from that point of view. It also makes easier filter realizations because, again, you don't have to overthink the design too much. You can very quickly come up with a reasonable approach. And it also leads to less sensitive designs. And this is related to the fact that, as you might recall in earlier discussions, when you try to make a very complicated transfer function, for example, something that may look something like this with many transmission zeros and so on, any little mistake you make in the fabrication results into relatively large errors in the transfer function. So with a non-resonating concept, this type of problems go away. Now, what exactly it means in the physical domain? It's basically a connection point in the filter. So this connection point can literally just be a node that you connect resonators to, or it can actually more generally be some type of capacitance or inductance that does not resonate in the desired band. So it has a smooth frequency transformation. And at the end of the day, as you can imagine, even a single connection point, when you make it in the layout, it actually represents some level of capacitance. So now how do we capture or model a non-resonating node into the coupling matrix framework? So there are two things there. One is that once you have a node in the filter layout and it's a non-resonating node, then essentially its self resonance will be set to 0. So the second thing is we have to modify the U matrix, and we have to modify the diagonal elements, because you might recall that all the diagonal elements, except for the ones that were related to the source and the load, were actually set to 1. So for the non-resonating node, instead of being set to 1, it will be set to 0. So let me give you the first example so we can kind of put all of this into practice. So let's say that we're trying to synthesize a first order bandstop filter at 2 gigahertz with this much bandwidth. So before we even go through the math, let me try to draw your attention to this diagram here. And if you have followed what I have been discussing so far, it probably won't take much to not only guess what this filter diagram is doing, but actually you could have synthesized it yourself without me saying anything. Essentially, you're looking for a bandstop filter, so you need to start from a node, from a pole here, but you can't connect this directly to the source, to the load path, because this will actually give you a bandpass filter. Rather, you want to turn this pole into a 0, so you want to essentially reflect this open at resonance to basically a short. And to reflect an open to a short, you need a 90-degree coupling section. So essentially, you start with a pole, you start with a resonator, you introduce a 90-degree coupling section, you bring this directly to the path from the source to the load, and because this is going to be a first-order filter, they only need a connection point there. In other words, you just need this idea of a non-resonating node. So again, it's a very intuitive idea. We can very quickly, just by somebody telling you, give me a filter with these characteristics, you can actually draw this coupling diagram. Now, it may not be the best coupling diagram, it may not be the best filter approach, but at least it's a reasonable starting point. The specific transfer function we'll try to synthesize here is actually shown right here, which basically has a single transmission 0 at omega is equal to 0, which when we scale this through the bandpass transformation, this guy will be scaled at the omega naught, the resonant frequency, which is basically 2 gigahertz. And we will assume that we want basically a 3 dB bandwidth, so we need basically the 3 dB points to be at plus or minus 1 in the normalized domain, and then we'll basically get them to represent, with an appropriate scaling, a bandwidth of 100 megahertz. Now, we have the coupling diagram, and now we have to represent this in our math framework, in the coupling matrix framework. As I mentioned, there are 2 changes we have to make compared to what we have done so far. One change is in the U matrix, and is actually shown right here. So remember that for the discussion we had last time, all the elements of the U matrix in the main diagonal were actually equal to 1, except for these 2. So these were set to 0 no matter what. Now, if you go back to the coupling diagram, our node 1, which is right here, is a non-resonating node. So we will go ahead and change the node 1 from a 1 to 0. Of course, node 2, which is represented right here, this is actually indeed a resonating node. Let's go back here. So node 2 is basically a resonating node. So this will remain equal to 1. Now, for the coupling matrix M, normally we would have a choice for these 2 numbers. If, for example, we had a non-synchronous filter, this guy might have been different than 0. Here we'll assume we have a synchronous filter, so this guy will actually be equal to 0. This one represents, though, the non-resonating node, and that means we're going to set this equal to 0. So these are essentially the 2 main changes we're making into the coupling matrix framework once we are dealing with non-resonating nodes. Now, everything else is very similar to what was discussed before. We will use some type of symbolic calculations to calculate the S21. And then once we have the value, which is the one right here, we will set this equal to the desired transfer function. And so now we will calculate essentially all the coupling coefficients. So if you go through the math, the coupling coefficients are actually shown right here. So the coupling from, for example, this is the coupling from the source to the non-resonating node, and so on and so forth. And that actually gives you the exact response you want. The last thing that is left is to basically utilize the bandpass frequency mapping that we covered before, and it will basically shift your entire frequency response, which is shown here, to the desired domain. So it will shift basically to a resonance of 2 gigahertz. And if you calculate actually the 3 dB bandwidth, which is between these 2 points, it will actually be equal to 100 megahertz. Now I'm going to go through the rest of the examples quickly, since the technique is identical, but I will try to point out a few interesting points. So again, without even reading the specs that we're trying to satisfy here, if you look into this coupling diagram, it doesn't take much to realize that first this represents a bandstop filter, and it represents a third order bandstop filter, since we basically have 3 poles, 3 resonators in this design. We have 3 non-resonating nodes shown right here that are basically supporting those resonators. And once you label everything, as I have done here, then you can go ahead. By the way, this is the response in the normalized omega domain. And this is there to, again, show you that we are starting with a coupling diagram that actually has the required response, except that it's scaled to the normalized domain. So then we're going to go ahead with a coupling matrix. You can very quickly validate what I just said before. For example, here you will see that only nodes 2, 4, and 5 are the resonating nodes, and everything else has been set equal to 0. And all the main diagonal points here are equal to 0, but for different reasons. We have a synchronous design, and also all the non-resonating nodes have been set equal to 0. Then after the math, we have all the coupling coefficients here. Once again, I am ignoring phase responses, and so that's why plus or minus will not make a difference in these calculations. And once you do the frequency mapping, you will take this desired response and simply scale it to the area that you want. This last slide, I wanted for you to just have a quick look. We're not going to go through sensitivity analysis in this class, but I do want you to realize that one of the great advantages of this coupling matrix approach is that you can separate the effects of different things. For example, in this example, I'm showing you what does a change in M12 and M13 do to the frequency response. M12, if you go back to the figure, here's the M12. So M12 is a coupling between basically the filter structure and the first resonator, and similarly, the M13 is this coupling here between the first 2 non-resonating nodes. So if you're interested in, or worried, what will my filter do if I make a mistake, a fabrication error, for example, you can very quickly isolate just these 2 effects and then replot the frequency response that you see here. So for example, you will see that with the M12 here becoming higher, you're basically broadening your bandwidth. And so you need to be prepared that if your M12 is increasing, your frequency won't change. The frequency will be impacted only by the resonators, but the bandwidth will increase. This is also very useful in, let's say, the post-fabrication analysis. If you don't hit the right bandwidth, you don't have to start analyzing every single possibility in the design. Rather, you can very quickly say, okay, I really have to tune that coupling to get the right bandwidth. All right, example 3, I just wanted to also think a little bit about what this coupling diagram might do. It's a coupling diagram that basically has 2 resonators, and it has those resonators in the direct path from the source to the load. But there are basically 2 paths, and it's a very good and easy way to realize a dual passband filter. You may remember that many of the current communication standards actually require dual bands or 3 bands or 4 bands, and so that's one way that you can do that. And it's actually one of the easiest ways you can make multi-band filters. And this arrangement is actually called transversal arrangement. Essentially, you're simply connecting more nodes, more resonators from the source to the load as you keep adding bands. So in this particular example gives you a specific transfer function that we want to implement. This is the response in the normalized the frequency domain. So this is the first passband, this is the second passband. And once you go through the technique and through the same math that we have been discussing so far, you will basically find out that you have the 2 passbands. Now, the 2 passbands in this particular example are not greatly defined, are not as sharp as you would like them to see, but that's because this is just a first order filter. So each band has only 1 pole. You could actually make more poles and get a sharper response for each band. This is the frequency transformation that we have applied here, the normal bandpass transformation. And the fractional bandwidth that you will see here is actually related to how widely you want to separate those bands from each other. This is an interesting example that kind of teaches you how you work with cascades. So a lot of papers in the literature follow this type of ideas. In this case, we want to basically make a combined bandpass and bandstop response. So we want specifically to introduce transmission zeros at some frequencies. This is the frequency that we're talking about here. And you want to have a specific bandpass. So you can do that by simply cascading a bandpass characteristic, a bandpass response, with a bandstop response. It's a very, very easy way to basically do that, again, by using a non-resonating node to connect things with. And again, once you go through all the math, this is basically the final frequency response that you will get in the denormalized frequency domain. So here you can see very easily the two transmission zeros that we have, and this is the passband of the filter. In this example, I want to show you a little bit more complex response, and I really want you to look at this with some type of pride, because now you have so much knowledge in this field that even if somebody draws this type of a coupling diagram to you, you can very quickly identify what the response here is. So this is, again, a resonator that is basically reflected twice until it hits the signal path. So clearly we're talking about the bandpass filter, and because there are two of them, and they can be tuned to two different frequencies, you basically will have a dual bandpass filter. So you can choose, for example, one of these resonators to resonate at 1.8 gig and the other resonator to resonate at 2.2. This is an example where I'll show you a specific realization, so you can see exactly how we make this. So try to keep this coupling diagram in mind. The math is identical. And once we basically calculate all the coupling coefficients that are basically down here, and we will get the response you see at this point. So notice again that we have the bandpass transformation. This number here will control how far away the frequencies are. In this case, we know what they are. It's 1.5 and 2.5 gigahertz. And you can very clearly see the response of this and a nice transmission zero in between, essentially separating them. Again, this is an example of how sensitivities in couplings and frequencies can basically can actually be seen in the frequency response.